Hello, Water Resources. We're back to talk about climate change. We're going to start with some indicators, some of the observations that we see as scientists and observers that indicate that the climate is changing. So first of all, on this graphic, we have some example climate indicators. In this case, there's 10 different ones. Up arrows here in the white, those indicate that that indicator is increasing. So things like the amount of water vapor in the atmosphere, air temperature over oceans, the temperature of the sea surface, sea levels going up, and so forth. Black arrows that are pointing down indicate decreases. So these are things like the decreasing volume uh, of glaciers and ice sheets on continents, the decreasing coverage of snow cover in the winter, decreasing amounts of sea ice. This is the annual temperature anomalies graph. We covered this in its own video because these temperature anomalies, the data, and the trends that are shown on this slide are so important, it's got its very own video. So if you haven't watched that, go back and watch that video. Okay, let's talk about some of the evidence for rapid climate change. So climate change has been increasing in its rate all over the world. There's lots of data that support that. In fact, as I say in the slide here, the data are compelling and broad. I mean, basically all climate scientists agree that the climate is changing. Some of those changes include a warming Earth, the changes in precipitation patterns, um, and other things like that. Furthermore, basically everybody agrees that these changes are being amplified and exacerbated um, by human consumption and burning of fossil fuels over the past 150 years. There's really no debate about this in the scientific community. Now, there is debate in the scientific community. The debate's about the finer points of how certain parameters are changing, how much they might change in the future, and things like that. And a good example um, is sea level. We'll look at that in just a moment. Okay, so global sea level. We know that it's changing. If you look at the graph on the left here, from 1870 to 1990, we saw a rate of change of sea level. It was increasing about 1.7 millimeters per year. Multiplied over a whole century, that's about 6.5 inches of sea level rise. Now, if we look at the data just since 1993 up through about 2015, we see that that rate is almost doubled. Now the rate is 3.17 millimeters per year. When you extrapolate this out, even if you just assume that that rate of 3.17 doesn't change in the future, that's more than a foot of sea level change in the 21st century, in the current century. But what we know from various observations is that that rate of change continues to increase, meaning that sea level continues to rise faster each year than it did in previous years. Now, this is an area of debate, though. We know there's no debate that the rate of sea level change is increasing. Um, what we're uncertain about is what that's going to mean in the future, how much it will continue to increase, what the overall rate for the 21st century would be, and as a result, there's uncertainty in the scientific models and in other data sets about how much sea level we'll see this century. It looks like we're going to get at least a foot, but it could be up to 3 to 4 feet, which is really, really significant. Global temperature rise. We talked about the global temperature anomalies. Um, we know that temperatures have been rising all around the globe, so I won't dwell on that here. But I will reiterate that the warmest years in the record are the most recent years. And over the last 20 years, our coldest year is warmer than any year in the previous century or more before that. So climate change not only is something that's going to happen in the future, it's something that's already happened. It's happening now and it will continue to happen. All right, so we looked at that global anomalies over land and air earlier in this lecture and in its own lecture on that anomaly chart. This is that same graph, the same global anomalies, but right now we're only looking at global ocean temperature. So this is just the temperature of the water. It's not the temperature of all the oceans and the land. Like that other one. But the point here is we're getting the same signal. When you look at this graph, I think without seeing it side by side with the global ocean air temperature anomaly graph, you wouldn't be able to probably tell which one is which because the pattern is very similar. It's essentially the same, but that's important. That means that the signal that we're seeing on the continents, the signal we're seeing integrated over the whole globe, the signal we're seeing from the ocean are all in sync. They're all moving in the same direction, which is what we would expect um, if the climate is changing. Shrinking ice sheets. So this refers mostly to Greenland and Antarctica, which are the large land masses that have significant ice sheets. Both of those ice sheets, and one's in the northern hemisphere, one's in the southern hemisphere, both of those ice sheets, the volume is decreasing. There's a net melt. We lose more ice every year to melting than we gain from new snowfall being compacted into new ice. That's contributing to sea level change, and we talked a few moments ago about possible or about an actual 6 to 7 inches of sea level rise in the 20th century and a potential foot to 4 feet sea level rise in the coming century. Most of that's going to be driven by the melting of these large ice sheets. Now, separate from ice sheets would be glaciers. Glaciers that are what we call montane glaciers. These are glaciers that form in mountains. These are common in the Alps in Europe, in the Rockies, the Northern Rockies in North America, various mountain ranges in Alaska, the Andes in South America, the Himalayas in Asia, all over the world where we have high mountain ranges, we have glaciers, and people have used and depended on those glaciers for water sources for hundreds of years, and as such they've tracked their changes and the extent, the length of the glacier, the volume of the glacier, and so forth over those times. So we have some really long historical records of changes in these glaciers. And when we look across the Earth, if you look from 1966 to 2005 here, all of these changes are negative percentages, meaning that the glaciers have shrunk. Now there are a couple of counter examples in the world. There are some glaciers in southeastern Alaska that actually have grown during this time period. So they've moved in the other direction from virtually every other glacier on Earth. And even that exception is well explained by a changing climate. Those glaciers in southeastern Alaska that have had net growth, what's happened there is the air has warmed, but we're talking about really cold air. It went from really cold to not so really cold, just cold, but still well below freezing. And as you know, warmer air holds more water vapor. Water vapor can be precipitated out as snow when the temperatures are below 32. So since in southeastern Alaska we went from a temperature well below freezing to a temperature a little warmer than that, but still well below freezing, what we're seeing is more snow because of the slightly warmer air, which can hold more water vapor, and so that's causing the glaciers in that area to increase. So even the exceptions to the overall global trend about the shrinkage of these glaciers actually fits well with the interpretation of global climate change. Arctic sea ice. Now, Arctic sea ice is different than when we talk about the continental type glaciers that are on Greenland and Antarctica. Those glaciers in Greenland and Antarctica are on land. So when that ice melts, it runs off and increases sea level by adding water to the ocean basins. The Arctic sea ice, this is sea ice that forms over the Arctic Ocean. There's no continental landmass over the North Pole. It's an ocean. And just like if you have a glass of iced tea and you have some ice in it and the ice melts, it doesn't cause the glass to overfill. There's the same amount of water in the glass, whether it's partially frozen as ice cubes or if it all thaws out. So the melting of the ice in the Arctic doesn't increase sea level in and of itself, although it does have some indirect effects. Um, but that Arctic sea ice is really important. During the winter, that sea ice expands and covers a greater portion of the Arctic Ocean, and then in the summer it always melts back a little, but in recent decades it's melted back a lot. That means that in the summer, when there's 24 hours a day of sunlight shining on the North Pole, in the past we used to have a lot of ice cover. That white ice would reflect that sunlight back to space and prevent it from warming the Earth. But now, as you see here, as that Arctic sea ice melts, there's more blue ocean. Blue ocean is darker. It actually absorbs the sunlight and then converts that to heat instead of reflecting that sunlight, that solar energy back to space. So that causes the ocean to warm, that causes more sea ice to melt, that causes more warming. Ultimately, this has resulted in the Arctic and the surrounding land here in northern Canada, Alaska, Siberia, and so forth is where we're seeing some of the most rapid changes in global temperatures due to climate change because of this change in that climate and in the Arctic Ocean. That has global implications though, because if we're warming the Arctic, that also means we're warming Greenland, which means we're melting those ice sheets, and when those melt, they do contribute to sea level change. Now let's look back and think about just extreme events like record high temperatures, record low temperatures. If we had the hypothesis that the Earth's climate was not changing, that it was steady, what would we expect? Think about that for a moment. We would expect that, you know through your experience that we have some unusually warm weather, we have some unusually cold weather, and if the climate wasn't changing, we'd expect to see those in about equal amounts. We'd have some extreme warm events, some extreme cold events, and probably over a longer period of time, like a decade, we'd see that there'd be about equal high temperature records and low temperature records. So that would fit with this hypothetical division of record highs and record lows over here in the absence of climate change. We'd expect about 50-50. In the 1950s, we saw about 50-50. About 52% of records were highs and 48% were lows, so pretty much right on the mark. You'll remember that when I talked about the global anomalies, temperature anomalies, that the 1950s are where that century-long warming trend intersected the average temperature for the century. So during that time period, because the increasing trend intersected the long-term average for a few years there, that means that if we had like slightly warmer weather, that would be a record warmth. If we had slightly colder weather, it'd be record cold. So in the 1950s, these records sort of evened out. But since then, if we look at the 1980s, 90s, and 2000s, and I have some graphs here from the 2000s, we see that the predominance of records are the record highs. We still get some record lows now and then. There's more going on here than just climate change. Other things influence our day-to-day weather. But because climate controls the long-term signal, what we're seeing is in some years, like 2012, which was actually at the time, 2012 was the warmest year to date. That record's been broken many times by subsequent years, but 90% of the records that year were record high temperatures. Other warm years like 2010, 2011, about 3/4 of the records were high temperatures and only 1/4 were low. 2009, which was still warmer than almost any other year previous to it in the record, but cool relative to what we've seen overall in the 2000s, there we only had about 56% record highs. So we still have variation year to year, but more years than not, we're breaking highs, not lows, which is exactly what you would expect if the climate was changing. All right, so we'll leave it there for our climate change indicators, and in the next lecture, we'll talk about a broader overview of climate change and what's happening, and I'll see you then.